شوف واش لايف خدام. Alex, do you have the thing that has multiple USB ports? Do you have it?
Like that?
Yeah. Can you give it to me? Type C.
Is it the edge or
Half. It wasn't my thing.
because it's not completely my place.
Else we did it.
So it will different.
If you want to. Okay, just on this side.
Qui traqué. On trouve les bras qui traquent. الصوت شي خدام فين كاين وتسناو راح ما يدخل
Let's camera just some sector.
That's right.
All the
This
sector.
is better because if we do.
Yes, we did.
Yeah, no, I don't think about this. Oh, she's in your phone. Like, I'm taking pictures from this side. Like, for example, I'm checking it.
Rather than stick.
He was like, let's wait 10 minutes and then we start. Someone
But I mean, thinking. So it's
With you guys and also.
so both playable, so we can keep it. So we can shoot it.
Like, even though it's right now. Take a picture of you.
Mistaken, I don't know. I never used it, so
let's try with from it.
yes. Let's do this. It's interesting.
It glitched because we're both now in the. I don't know who to follow. So the only one person
Yes. Now you speak, so it focus on you. This time, should it follow me?
Yes, it did. It did. Where's my device?
It's getting sassy. Sassy. The girl behind you. Ask her if she. Yeah. It's okay that we post pictures.
نجبد في كاميرا غادي يبان دوكا رجعت للور.
لا هي اللي بانت. اوكي فهمت. سامح.
I think it's good. What's this story?
See you.
Just now testing. The microphone here.
The microphone is down.
Yes. So it okay that I'm talking now. And
Yeah, just like. برا كيف تمشيها برا في القسم هنا حيت مرة ايفن باش تلقى شحال من واحد برا كيدور جوج.
Keep that for yourself. Yes, yes. They have to be.
Average strukturze. Ничего будет.
Dude, yeah, there's nothing. I was off actually waiting. But the thing is just that last year.
Сейчас прям там март. И вообще просто семестр сколько часов?
You know, my friend liked you. My friend had a crush on you. She was very she was so pretty. You were really nice. But later I stopped seeing you. Yeah, you disappeared.
I feel like
But like really? At a different time. You're like, what are you at? Where are you? I'm like, the people go to the bathroom, what? I don't want to. Really on the topic, like, but I wish it kind of it's like perfect. I wish it was actually better. I wish it was. He was not I will. Yeah, I can. Girl, how you sleep? She's That's oh yeah. I'm sorry.
Я должен учиться.
I started eat meat. Like I survived. I'll see it perfectly. One matters.
Китайский легче. Значит, у тебя P1 китайский видео. Языке. Ой, язык учишь новый.
The book. What's the thing? It's rock.
No. So, hello everyone. Hope you're all doing well today. I'm very happy to see you all today to assist to Professor Ivan's talk today. But I see some old faces and I see some new faces, and I hope you don't mind I introduce myself first. So, I'm Ahmed Mari, computer science major, math minor, and the president of the Mathematics Society in Construction University. So then you may wonder, what's the Math Society itself, right? I mean, good question. So what's the Math Society? Within the Math Society, we believe in three words that are namely think, calculate, and create. Why? Because we think abstractly, calculate to make our ideas precise, and finally create stuff that were never created before. And how do we do that? Well, through multiple events. For example, some of you may have assisted to our series of the math behind. We had the math behind AI, machine learning, neural networks. We had the math behind poker and game theory given by Professor Kevin. And we had the math behind interstellar. Not only that, but last week, we had the math behind cryptography and cybersecurity. Not only that, but we also have our series of very famous series that is called the Undergraduate Seminar. We had the Undergraduate Seminar 3, where we talked about golf modeling, string theory, and drone irrigation optimization. We had then the Undergrad Seminar 4, where we talked about dark energy and acceleration of the universe, Benford's law, and Rajkota methods for neural networks and differential equations in AI. Then you may ask, what's even the Undergraduate Seminar? Well, to explain for the new people, the Undergraduate Seminar is an opportunity that we give to students where they can apply and get accepted to prepare in a span of 3 weeks, a research project supervised by us, the Math Society cohort, and one selected professor depending on your selected subject. this undergrad seminar is the right opportunity for any students, first year, second year, third year, to have a very well-certified project on his portfolio and to develop a very, very rare skill that we struggle to find nowadays, the skill of researching. That's why, and why am I doing this today? The reason is, today we start and open the application for the undergraduate seminar, which will happen soon. Anyway, it will happen soon. So if you're interested in that, and if you're interested in making your research project with us, then don't hesitate to apply. Moreover, we don't have only the undergrad seminar for as our next event, but we have some other events too. For example, next week we have the correlation theory and the math behind causal machine learning. And the week after, we'd have the math behind finance and pricing, which will be in collaboration with the IBCM Society. And not only that, but really because we're preparing a datathon, an alumni talk, and the next guest was going to be the alumni, and finally, the undergraduate seminar 5, which will be the only undergraduate seminar for this semester. Before finishing this introduction, I would like to mention one thing. Previously, in our first semester, we had what we called the Math Support Center, which was basically a weekly thing that we used to have each Saturday, where students were welcome to come, and we would explain them any possible math subjects there. And namely, the tutors were mainly me, Pablo, if you know him, Lordana, etc., etc. So, again, quote unquote, pretty much the very good qualified students, if I can put it that way. The problem is, we have, if I can put it that way, a shortage in tutors this semester. So in order to be sure if we should continue this event or not, if you are interested and if you want the Math Support Center to still happen, please scan the QR code, which I'm going to do for 15 seconds approximately, when you find the vote for either continuing or not continuing the Math Support Center. And depending on how many people would have voted for and registered to come to the Math Support Center, we'll decide accordingly if we would keep it, not keep it, weekly, bi-weekly, and so on and so forth. So if anyone is interested, please scan the QR code now. Anyway, I hope whoever wanted to scan it was able to. And if you still want the link, don't hesitate to ask me. That was pretty much what I had to tell you today. So be ready, because in a few minutes, we'll start our talk. Thank you very much.
Yeah.
Get seminar.
So yeah, hope you're ready. And please have the crowd of applause for Professor Ivan.
So is recording already on, yes?
Yeah.
Hello everyone, and I see there are many faces of people who don't attend my courses, so
maybe didn't meet before. So my name is Ovysanikov. I'm lecturer in mathematics, and I teach some math courses here. And I'd like to introduce here my topic, which will be about chaos. So this is a very complicated and mathematical topic. So let's try to do it really balanced, such that I hope we will understand each other. So it should be understandable. So I hope you will understand what chaos is without doing many formulas. So let's pause this task. And so I didn't prepare slides for that. So let's make it dynamic. And we will just talk about it. So first of all, let's introduce the topic, the big topic. And this is called dynamical systems. So in dynamical systems, we study the evolution of systems. And the system can be some vehicle, maybe a plane, maybe atomic reactor. It can be some economical system, say economy of a country, or some other, or maybe a population of certain species on certain area. So a dynamical system can be anything that has evolution. So something that changes in time. And the main thing is that the dynamical system generally is described using differential equations. That is, I write x dot equals f of x, in which x is regarded as a state or position, and it really depends on what we are talking about. So if it's maybe a motion of a particle in space, then we look at 3 coordinates. So if it's something that in really space outside of the Earth, some traveling object, then we may look at 3 coordinates. Then x will be 3-dimensional, so the position. But if we write some Newton laws, then due to the accelerations, we can also velocities included. So it can be 6-dimensional in that case. Or if we speak about, say, interaction of wolves and deers in some region, then it will be 2-dimensional. So then the state of the system will be, say, number of wolves and number of deers, and then these numbers will dynamically evolve somehow. So this is it. So x can be of any dimension. But you don't have to imagine 4 dimensions, 5 dimensions. So just please accept this as a fact, as many other things that I will say today. And x dot here is the time derivative. So this is just the simple notation. And time derivative, so I hope that you have some basic understanding of what derivative is. Simply speaking, this is a velocity. So the derivative is the velocity, how the variable x changes. And now we have the relation that the velocity is some function of the position or of the state. What does it mean? Assume that we are dealing with a plane. So we are speaking mathematically in R2. So we have this plane as our phase space, which describes all possible positions. And assume that now we start with some point. And if we have some initial point, then we can evaluate the function, whatever the function is. Then we obtain some vector, because it will have 2 components. And now we have the velocity that applies to this point. So in this point there will be a certain velocity. This means that we can move forward if we know the velocity. So we move somewhere, but then this is a new point in which we can evaluate our function and obtain the velocity again, then move, then obtain the velocity again, and then we obtain a trajectory. But also we can go in the direction opposite to the velocity, and then we can compute the prehistory. So this is like the past, and this is the future. Okay, so given a point, just now please accept is given any point, We can evolve it in forward time, we can evolve in backward time. So every trajectory is some curve. And now let's think, what kind of curves can we have? Basically, mathematics and its branch topology distinguishes two curves, only two types: unclosed or closed. Okay? And no other options are in math, in any dimension. So this is very simple. And actually, in addition to these two, we have another type of motion in which we stay forever in one point. This is if we put our point in the place in which the function is 0, then the velocity will be 0, nothing moves. Then we stay there forever because the velocity also doesn't change. This is called an equilibrium. Okay, so the equilibrium point is a point in which we have no motion. And now we have only three possible types of evolution and nothing else. So this is very simple explanation what do we have in dynamical systems. But where does the chaos come from? It comes from the structure of how these trajectories can exist in the space. So now can you imagine that we have a three-dimensional space, and now we take any point, and for every point we build a trajectory. We can imagine that so 2 points can belong to a single trajectory, but if not, then these trajectories will be absolutely separate curves. And now can you imagine, we take the whole space, we take every point, for every point we build a trajectory, then we decompose the whole space into curves and maybe points. And the structure of those curves can be complicated. Then we come to the chaos. Especially when we are dealing with the plane, then every curve, see, it can be unclosed curve or closed curve, it divides the plane. So now, when we have one curve, then starting from this point, we cannot evolve outside. Because the trajectories cannot intersect. Because if they intersect, then there will be a point in which we have two different velocities. It's not possible. So it means that on the plane, one curve separates the domains, and on the plane, generally speaking, we have regularity. So on the plane, we cannot get chaos. So it's a bad news for you. You have to imagine 3 dimensions for understanding of chaos. So plane is not enough. Okay, so this is the introduction of our topic in principle. And then I'm going to discuss how of these curves we can compose the chaotic motions. But first of all, before speaking about chaos and understanding what it is, let's ask the question, what is not chaos? What do you think? So, when we can say that something is not chaotic. So what are associations with not chaotic, yes?
If we can predict what is going to happen, then we can say it's not chaotic.
Yes, so absence of chaos means predictability. And when we speak about predictability, we come to physics. So if you imagine, say, Mercedes factory, they produce several cars of the same model every day. But if you take 2 different cars, are they the same? No. Why?
Technically,
Yes, so of course they are produced on the same machines. Yes, but if you take one car, then some piece will be a bit bent, so maybe one or maybe
influence of
1/100th of grad a bit bent. Maybe here there will be millimeter plus, millimeter minus. Maybe the color will be different. So if you take 2 different cars, they're generally different. So how can we drive them if they are different?
They're predictable enough.
Yes, because they're predictable. So it means that the mistake doesn't matter. And this predictability can be explained with this simple experiment. So if we have some some profile, maybe some bent plane or whatever. If we drop a ball, then it will go down. And then it will move, maybe bounce, maybe travel here and there, but the position at which it will be standing and not moving, the equilibrium will be here at the minimum. Okay? And now, if we now think about it as a huge system, again, maybe the economy of some country, then this equilibrium is some regime in which everything works predictable. And there is nothing ideal in our world. This we know. We do measurements with tolerance. Yes, we make mistakes. Even if I say, take some of you, give you 50 euros and give you a task to press one button 1,000 times. Those presses will be different. Sometimes you'll press at the middle, sometimes you'll press at the edge, sometimes you'll press that the contact will not be connected. So these 1,000 presses, very, very simple task, but they will be different. Yes. But if the result that we need is like connecting some contacts, then likely it will happen and some device that is connected will work and will work in the same way. That is, if we place our ball not in this position but somewhere nearby, then this mistake will be eaten by the system itself. So the ball will fall down and it will tend to be here. Maybe it will oscillate nearby, but it will be something controllable. So this is how we can imagine predictability. So this is a stable equilibrium. Or generally speaking, an attractor. Okay, so which means that the system itself evolves towards this state. So we cannot control it. Yes. So, for example, if this is our nuclear reactor, and then a tram comes by, then some states are perturbed, but then itself it will stabilize. So it will go back. So we have this predictability. Yes, and so this is like shooting. So every day we start this, say, reactor, or maybe we start the engine of our car, and it starts in different conditions. So different temperature every day. So some different wind, maybe different level of oil and everything. So we start our engine in different positions every day, but what we expect, what we predict is some stable work of this engine. So this is what physicists want to have, what engineers want to have, because this is where we rely on them. So on the devices they produce. So this stability and some predictability that guarantees us this result. But what if our plane will be like this? If we put here our ball, it will fall to this direction. If we put it here, it will fall on the left. Okay, then let's analyze. Okay, we are all researchers. So let's change the position, and then we put the ball and see falls on the left, on the right. So we have right points, we have left points. So now we can have some predictable behavior that will escape. But there are two types of escapes. So there is right escape, left escape, and the evolution is principally different. But now we have left domain, right domain. The domains have a property because they have the common boundary. So two domains meet at a point. And what happens at this point? This point may belong to the left domain, to the right domain, but we all know, maybe from physics, that this is a position at which the ball doesn't move anywhere. So this is an equilibrium. What's the difference between this equilibrium and this one?
That one is unstable.
This one is unstable, which means
Might go to either direction.
anything happens, like a butterfly flying in South America, and this ball will fall to the right or maybe to the left, we don't know. Okay? So any small perturbation kicks this ball out. So basically, this state cannot be observed in the experiment. Because if we do the experiment, it is likely for us to land in this domain or this domain. And there is probability 0 to start in this position. And even if we start, then any perturbations or anything happening outside, maybe in kilometers, will make the perturbation and then it will fall left or right. So this is an unstable equilibrium. So unstable equilibrium is something that we cannot see at experiments, but they play an important role because any real system, okay, if we don't speak about explosion, but explosion can be also regarded as an attractor, so like the system comes to it. So here we have this unstable regime, but when our system goes to the right, goes to the left, then it is likely that it will go to some attractor, to something stable. Just here it will converge to something, from one object, here it will converge to something else. And they will be two different objects.
What is the explosion attractor?
Explosion is an attractor in the sense that if we describe our system in some variables, then the explosion may be not describable by them. But if we think that we want to make this explosion possible, maybe we introduce some variables before, and immediately we increase the number of variables, and then in this extended space with dimensions, maybe this explosion will be describable. Because if we, this is a problem of engineering, actually, because we can think about some stable solutions, maybe see the evolution, maybe appearance, disappearance, but if accidentally our stable solution disappears completely, then our system will fly to the nearest attractor, and this attractor can be catastrophic. So with this, we should start speaking about not just a system that has some stable and unstable objects and some evolution to them, but also about parameter dependence. And bifurcations. So maybe you heard about bifurcations, maybe from some journalists, so the meaning of like news, of bifurcations written in news is a bit different to what we understand it in math. But in general, bifurcations happens when some regime that we expect is replaced by some another regime. So we start seeing something else. And this can be explained as follows. So it happens when our system depends on parameters. That is, when we have the velocity that is a function of the position and something external, some external constants, and we can think about it like some controls that we can tune. So we have some control panel in which we can tune some numbers here. So mu can be some several parameters, and when we tune them, then can you imagine? Now, when we fix some parameters, we have the whole space divided into trajectories. But we tune some parameter, and the whole structure of the trajectories changes. Okay, so just one move of some switch changes completely the structure of the whole space, existence of our reality. This can be demonstrated in the following way. Assume that we have quadratic equation. Then we can compute the discriminant, which is b squared minus 4ac. I mean, you are from different countries. Somewhere we compute this, somewhere we compute divided by 4, but there is this quantity, and if this quantity is positive, then we have two roots. Okay? So this is a fact. But if these coefficients come from data, from measurement, from some physical experiment, then we know them with tolerance. We do some mistake in measurement. But if the discriminant is positive, then when we measure the coefficients with mistakes, then still qualitatively we have the same situation. So maybe the real roots will be not there, but in some other positions. But this discriminant, which will be positive, say we compute that it is 10, but actually it's 9.5, but still positive. So qualitatively we see the same picture, even though the position is different. The same happens when it is negative. Then we have no roots, and again, if you make a mistake in the measurement of the discriminant, then the graph of our function will move up and down, maybe breathe horizontally, maybe move horizontally, but qualitatively we have the same picture. So if we are physicists, then we see like we produce two cars, and one car works with one speed of the engine, another car with a bit slightly different parameters, because some pipe is a bit more dirty, some other slight changes. Then it behaves, but again, predictably, but a bit with some other parameters, just as a fact. And here also, absence of roots is something that is preserved under small perturbations. Okay, now I hope you understand what it means, because this is a mathematical statement. So something is preserved under small perturbations, the qualitative picture, like this. So, again, like our discussion before, between these two structurally stable cases, we have the boundary. And what happens in this case? If we know coefficients with some mistake, with some error, then it is likely that actually we don't have this situation. So if the situation is like this, then we do the measurement, and instead we see either this or this. Okay, because these are domains, and this is just a boundary, just one value for this discriminant. Okay, so this is something that we cannot observe, generally speaking, if you make mistakes. So this case is called structurally stable. So not stable in the sense of attraction, but structurally stable is that this picture survives small kicks, small perturbations, maybe some shaking or whatever. But this case generally does not survive. And so when we start shaking, it may move down a bit, up a bit, and we have principally different situations. So this we call it bifurcation. Okay, so for physicists, usually the bifurcation is the process of transition. So we change the parameter, like we tune some. So, say this can be the value of the discriminant. We tune it, so we go to the negative value, and then we see that the parabola moves, then 2 points collide, and then parabola detaches. So we can see this as a process. But the system, this reactor, may evolve somewhere else, to some danger regime. So this is the general setup. When we speak about dynamical systems that depend on parameters, then we look at the evolution, how the trajectories, some specific trajectories, appear, disappear. In particular, equilibria, so, because this can be equilibria. For example, this one is stable, this one is unstable. Then when we start here, then everything is attracted. So again, we can make some mistake, and the system itself will converge to it. But this, for example, is unstable, so everything escapes. And if this is our reactor, then some parameters, some outside influence will keep us in this stable state, even if this state will evolve a bit. But if the parameters are changed too much, say 2 trams go past our nuclear reactor, and then this perturbation of this increased perturbation is such huge that we have the detachment. And then when these points disappear, then the domain of moving to the left disappears. Then we'll be in the moving right domain. Okay, so like this parabola is pulled up, and what is remaining is just going right. And our reactor will fly somewhere in which it will meet another attractor. And this attractor can be dangerous. And it will be a question, even if we see that we did something wrong and a tractor evolves, so our reactor evolves somewhere, we can say, okay, let's immediately return the old parameter value. So we return, these states are created, but our system is still there. So first of all, if we restore the parameters, it will not restore the catastrophe. Because now this boundary, like here, will be created. Yes, so this one. So if we are there and we create this bump, it is hard now to get there. Okay. So this is the general understanding of bifurcations and the dynamics and stability that we need to understand what we are talking about. So this is now the question of predictability and dynamics. Yes?
What about if the parameters, like it's the one with the negative? Which kind of system is this?
Actually, so the example of this system can be just x dot equals ax squared plus bx plus c.
No, I mean like if the parameter is less than 0. You said here is actually stable bifurcation. What's the last one?
It is that, so as I spoke before, so the zeros of the function are the zeros of the velocity and their equilibria. So if I just take this function and put it into the dynamical system, then immediately those zeros of this function will be equilibria. And this is immediately the example of such a system. Now if you play with parameters ABC, if you use the Runge-Kutta method to recreate the trajectories, then you will see that depending on the discriminant, we will be either attracted to this point or flying to the right, or we will inevitably fly to the right. Okay? And there is no way. So this flight will stay forever, so nothing will happen. Even if we switch parameters back, we will still fly to the right. So this is when the system becomes uncontrollable and comes to the catastrophe. So this is the moment in which planes fall down, reactors explode, and it's not fantastic. This is a catastrophe. So this is itself an interesting topic. It's not even chaos. It's some stability, but the structure of attractors is changing, and then we recreate the desired attractor, but it's not achievable. Okay, so this is some of the simplest scenarios of a catastrophe which describes some real phenomena. So very complicated catastrophes, very dangerous ones, can be described in some simple models. Okay, but this is about the stability, some more or less regular behavior, because mathematically this will be some regular behavior coming to an attractor. But it can be some high amplitude motion in which just the construction of the building will not, cannot hold anymore. But now let's speak about chaos and look at some example in which we will have chaos, and then we will see how it differs from the predictability. And before doing that, I will introduce so-called discrete time systems. This means that instead of velocity, we have the following situation. So this bar means x next. And now the idea of such systems is that, again, it can be some, say, plane. We take one point, we evaluate the function, and we obtain another point. But this is an instant jump. Then we evaluate the function here, we obtain another point, then another point, and then we have those jumps, so the trajectory is discrete. So this is called a mapping or a discrete time system. It evolves somehow discrete. So there is no continuous trajectory that connects. But again, if this function is invertible, then we also can construct the past. So if we can revert this function, then we can compute what happens before this point. But this is the future. And now, based on this, let's play a game. So we take a square. The square made of a paper. And then what we do, we squeeze it horizontally and extend vertically. So we obtain such a strip. And now let me mark that this side now is mapped to this one. Okay, so we do this operation. But now we do the next step. So again, we have our square. Now I will create chaos immediately here from this square, from this piece of paper. So just follow. So this is our top. So please remember this that we created here, but we bend it such that it lies on the square like this. So where is the top? Now it's here. So if I bend it to the right, then this top is now here. Now let's just decide that we are following only the points that don't leave the square. So it means that those points are lost. Those points are lost. Those points are lost. Okay. Let's now try to understand. So which actually points of this square will be lost? Now can we predict? So for this, we should imagine that what is not lost are these two stripes. Let's find the pre-images of those stripes here. And if we want to imagine the stripes, let's imagine their boundaries here. So what is the left? So if we take this stripe, where does it come from?
Side of the square.
So this interval is some piece of the interval here. This interval is some interval here. Okay? And this stripe comes with some horizontal line and horizontal line. So it lies here. Okay, so if I call it 1, then this is 1. So what happened to this stripe in the rectangle in the square, that this stripe was squeezed, extended, and also flipped. This stripe has the same structure. So when I mark this 0, then this 0 stripe came from this position. And this part is lost. So this was our top. And this top and the whole head is lost, the bottom is lost, and the middle is lost. Okay? And now we have that two horizontal stripes we are mapped into vertical stripes. So this was one step. So it means that this is like the domain of our mapping, and this is the image of our function. Everything else is lost. Let's try to imagine what happens after the second iterate. So, yes, so if I do the next step in this dynamical system, basically to imagine this, you need to, so look, we have this square, and this stripe is its image. It means that when we create from this square this image, then this horseshoe will become its second image. Okay, so when we make this horseshoe from this square, then this horseshoe will become the next object. Can you imagine that now this square becomes this stripe? It means that the horseshoe inside is squeezed, and then this horseshoe lies here and goes several times. So can you imagine this or not? So let's draw it a bit more carefully, and then we will speak what's going on here. So again, this is our square, and the horseshoe I will draw more or less thick. So now, if the square becomes a horseshoe, what happens to the horseshoe itself? Then it will be this one I will draw not thick, but just for you to follow. It will be this. Okay. Is it clear or not? So, I mean, you take both at the same time, you squeeze, you extend, then when this rectangle becomes this black horseshoe, then the black horseshoe itself becomes this double-banded horseshoe. It means that now we have, after 2 iterations, we have 4 stripes. And it is that now this stripe comes from the left part, so it has code 0, but now it comes to the right. So its origin was left, but now it jumps to the right. This one was the right and remains right. Then this stripe comes from the left and remains at the left. And this one was from the right, but was mapped to the left. So now we have 4 different vertical stripes with all possible encodings. And now you can draw it yourself. This is a nice game for kids. To try to imagine what happens after the next iterate. But of course we can imagine that there will be 8 stripes which we can encode by their evolution. And moreover, at every iterate we lose more and more and more points. So going forward and backward in time. So we are losing some either vertical space or horizontal space. It means that now if we try to imagine the infinity, so if we do it infinitely many times, then we will lose some part of the interval and we will obtain a discrete set. So now it will not contain any interval, because if we do it infinitely many times, every interval will be cut. So no 2 points will be connected by an interval. It will be a completely discrete set. And in this discrete set, every point never leaves this square. Because those who left are not interesting for us. It means that every point that stays there forever, it has some evolution. So every point at every iterate jumps to the left or to the right. So it means that every trajectory can be encoded by double infinite sequence of zeros and ones. Okay? So every trajectory can be encoded, and there is a theorem, so there is a rigorous proof that for every configuration there is exactly one trajectory that behaves like this. So we have one-to-one correspondence between such double infinite sequences encoding and the trajectories of that stay inside here. Okay, so now this is some chaos, because first of all, if we make a mistake, of course we will fly out, but let's imagine that somehow we know this whole set of points that don't leave it. But if you make a mistake, say if we follow this encoding, but at some iterate we make a mistake, then the evolution, our further evolution will be absolutely different. So the sequence of digits will be not related to what happens before. So now we have an absolute non-predictability. So we can follow, so given some encoding, we can repeat it, but vertically we have expansion. And expansion happens. So if we do, like, say, if the expansion in the length vertical is 3 times, it means that after 2 iterates, the distance between any 2 points will be multiplied 9 times. And then it will be 3 to the power number of iterates. So it means that every 2 points behave differently, because the distance will grow. So we can take arbitrarily close points, but after some number of iterates, the distance will be finite and they will be not related to each other. Okay, so the evolution of every 2 different points is absolutely different. Also, automatically, we have trajectories that realize this sequence. These are so-called fixed points. So the trajectory that always jumps to one side is actually the point that is mapped to itself always. So it just stays in place. It's like an equilibrium. So every iterate, these points come to itself. And we have 2 such equilibria here, but also the trajectory with this encoding is there. The trajectory with 110, 110 is also here 3 periodic. So it means that here we have infinitely many periodic trajectories with absolutely different configurations and absolutely different periods. They are here already. So this is the game in which we have such a chaos, in which we have infinitely many periodic orbits. And they exist already. This is our setup. Just unfortunately, this chaotic structure is not itself an attractor. So here we see that the trajectories escape from it. So basically, even if we have a system in which this structure is realized, and such systems exist, they actually appear in the neurodynamics. So the systems in which such structure of trajectories appear, they describe how our brain functions, actually. But specifically this thing can be not observed. Because we see that if we make a mistake, it is likely that we fly away rather than we see some dynamics. Because this set is discrete, it consists of points, and when we do measurements with tolerance, it is hard or impossible to locate the certain points. So this whole structure is unfortunately unstable. But already it is that we create some dynamics and you see that it's chaotic. So this, if you want to read about this is called the Smil's horseshoe. This is some example in which we can create a complicated structure. Now, about the attractors. So this comes from the experiment of Lorentz in 1963. So Lorentz was the meteorologist in MIT, and he wanted to describe the behavior, the convection in fluids. But fluids or gases doesn't much matter. So it can be the convection of heat in the atmosphere, or it can be in ocean and in the fluids. So he considered a simple model of a two-dimensional fluid. So it's just vertical fluid which doesn't have depth, I mean horizontal depth. So here we have our fluid, here we have some cooling, here we have some heating, which means that there is some temperature difference. If now this is the parameter, so we can tune it. It's really something that burns, and we can tune it. And when this parameter is very low, then the water capacity is enough to just conduct the heat. Okay, so the water is standing, not moving, and the heat goes through the water and reaches the cooler. But if we increase the temperature difference, then for some value, the capacity of the water is not enough to transmit all heat that comes from below. Then we have something else happens. So we work with this parameter, and what happens? It happens a bifurcation, which means that this condition of pure conductivity becomes unstable. So this state is lost, and something else appears. So the structure of trajectories changes drastically. So when the difference of temperature exceeds certain threshold, then we have some, say, detach of the parabola, and another solution becomes an attractor, in which the water starts moving in rolls. So rolls with certain widths are formed there, and now water starts circulating, and so it conducts heat, but also it brings. So now water wants to move due to this heating, and it moves and delivers the warm pieces due to the motion, so it can give some heat. So not cells given to cells, but now this hot cell goes up and personally gives this piece of heat to the cooler. Okay, and when we now play with this parameter further, so we tune it more and more and more, then the speed increases, but again, this capacity is limited, maybe due to viscosity or some other things. So at some moment, this becomes not enough. And what do you think what happens? We know kettles, yes? So we boil water every day. So they start boiling. So the next is that we have some turbulence. And turbulence means chaos, because if you imagine the boiling water, we cannot predict the trajectory of a certain piece of water. It's so chaotic, so it goes up and down, and it behaves very unpredictably, even from point of view of physics. So we cannot locate certain domain for which we can say this domain behaves like this. And what Lorentz did is that, so this is a big system of equations. This system is in partial differential equation. So this is derivative with respect to the height, with respect to the horizontal coordinate, with respect to time. So we have 3 different types of derivatives, and solving partial differential equations is almost impossible. So he did some reduction, some decomposition in modes, some Fourier transformation, and it was still, so he transformed these partial differential equations to ordinary differential equations, but infinitely many. And then he did what physicists do. Usually, so physicists like simplification. So from this system of infinitely many equations, he just took first 3. Without any explanation, but nevertheless, it happens in physics that we just simplify the model, so we cut our system and take just first 3 modes. And he obtained a system of 3 equations. Minus x, y dot is something, z dot is something. So system of 3 equations, and depending on 3 parameters. And what he observed, so this is a very, very, very simplified model of what actually happens here. So very simplified and even truncated. Nevertheless, when he started modeling, can you imagine the computational powers in that year? But there were some computing machines, and he did computations and found out that when this heating is huge enough, this is parameter r, so this is sigma, this is parameter r in front of r, and some other terms, and minus y, and here's something. So this r is related to this different temperature. So he fixed other parameters and was increasing r, and observed that for some value of r, there appears something. So the trajectory was regular, maybe periodic, maybe, so first of all, just equilibrium, so nothing happens. It's like the conducting state. But then when he increased this r, then the system came to a periodic orbit. So this periodic orbit became an attractor. So it's a cycle that attracts everything to it. But then he found that the trajectory started moving like this. It's just this mathematical system. And this is the trajectory of just one point. And this is what resembles the butterfly. And Lawrence called this the butterfly effect. So it's not only that the butterfly which flies in South America causes tsunami in Northern Hemisphere, but also the object that he observed himself resembles the butterfly. And this object is called the Lorentz attractor. Why? Because first of all, it's an attractor. Because this object he saw in the experiment. So he saw something very, very complicated, but it was observed because the system converged to it. So this is an important thing because then this is something physically relevant. So this is something that we can obtain in an experiment. We can reproduce it. And the important feature of this was that if he evolves one point, and basically, like for the Smale's horseshoe, when we have such type of evolution, we can take a point and just see it goes to the left or to the right. And also construct this one-way infinite binary sequence. And now, if we take one point and obtain its binary sequence, then we take another point nearby. And then it follows its configuration, but then from some moment the evolution differs, and then after this difference, the evolution will be different. And what is interesting is that if we are physicists, if we want to have predictability within this attractor, so we take one point, it has one evolution. We take another point, it has another evolution. Then, as experimentalists, we will do dichotomy. So, in between, we will try to find a point with similar behavior. So we have one point, another point, starting points, and the trajectory that in the beginning was just unclosed orbit. They are different in this configuration. So this has one behavior, this has another. We take something in the middle, trying to catch either these features or these features, but it has its own trajectory. Different one. Then we try to do dichotomy again. Half, then it has its own. It doesn't resemble this, doesn't resemble this. Then we take another point and it again delivers another configuration. So here we have the principal, so how to say, essential dependence on initial conditions, sensitive dependence on initial conditions. And this represents the chaos, so it's unpredictable. And at the same time, this Lorentz attractor is so-called robust chaos, which means that if we now in this regime of chaos and this attractor exists, then we can perturb slightly the parameters inside. The structure of those trajectories changes infinitely many times, but the whole object remains a chaotic attractor. So this is a robust chaos. This means that if we have the Lorentz attractor, we can measure the parameters with tolerance. We can measure the initial point with tolerance. We can even apply some noise, some external signal, which will be random. It is proved that the chaos will be preserved. Okay, so this is the chaos that is not destroyed under small perturbations. So this is very strong chaos. And also why it can be interesting, because chaos is not predictability, and from physicists we want predictability, from engineers. Chaotic attractor like this can be used for data encryption. So basically, if we take if we fix some parameter values and the initial point, it will generate us the unique trajectory. And this unique trajectory, for example, it's binary code, or we can make it, say, triplets, and then it will be the alphabet of 8 symbols or some other. Then it can be a key, and this encryption key will be unique, and just the recipient should know the same values and compute it on the same machine, of course. Because if we encrypt it using the trajectory, compute it in 4 bytes floats, and decrypt it, generate this trajectory in 8-byte floats, then we will obtain different trajectory. So this modeling of the attractor should be the same on both sides. But this provides a very strong, actually, encryption. And for this, it is important that this attractor is robust, because there are many other cases of attractors in which small perturbations destroy the chaos. And instead of chaotic attractors, there appear some stable orbit, very complicated but stable attracting orbit. And if you make such a mistake, if you encrypt your data with a periodic orbit, then the strength of the code reduces drastically. That's why the Lorentz attractor provides the strong encryption technique. And I think here I will stop. So just the models to observe the Lorentz attractor can be found on Wikipedia. So there can be some PHP code, HTML, Python, MATLAB, and other, in which you can just take this system and observe this attractor. And you will really observe. So this is an experimental fact. So thank you very much.
So thank you very much, Professor Ivan. So I have 4 things to tell you. First, please again a round of applause for Professor Ivan. Come. Second, I'd like to thank all of you that came today for this event, and I hope you enjoyed this talk. And I just wanted to remind you that this is not the last event of this semester, and that next week we will have our causation and correlation theory and the mathematics behind causal machine learning. And the week after we will have, in collaboration with IBCM Society, the math behind finance and how do we make risk-free profit and how do banks price options without looking at the future. And don't forget about the Datathon, UGS5. If you want to apply to the GS5, that's your time. If you want to make a project, that's the day where you have to apply for the GS5. And again, as I mentioned, the board team. If you are into tech, if you're into logistics, marketing, and if you feel like you have the skills enough to be accepted into the board team, don't hesitate to apply. Hope to see you soon, and thank you very much for today. And of course, any question? Sorry.
Maybe I just want to ask about the verification thing. So the main issue is that the change of state, right? Or the change of state from what is predicted, was predicted, to something that's not that's deviant, right?
So the bifurcations can be different, like, if, for example, if we have a stable state and we have some parameter. So we control it with the parameter, and then at some moment it loses stability. Then this point, so if it is stable, stable point, then if it loses stability, then, for example, there appears some periodic orbit around. And now this equilibrium becomes unstable. But then it will be that if this is our device, it's in some stable regime that we want, but then we increase too much the parameter, the device started vibrating. It can be a speaker or water pipes, probably you heard when you turn the switch on the water, they start vibrating. But then it's controllable because now we have vibration instead of what we wanted. But then, okay, something wrong happened, we turn the parameter back, and then this bifurcation comes back, and we are still here. So this is safe transition, so safe stability loss. But there can be another situation in which we have again the trajectory, again we have the same parameter, and this point loses stability, but in another way. So somewhere around there is an unstable cycle, such that it repels trajectories. But the loss of stability at this moment can happen that it's like here, the cycle flips in, but here the unstable cycle flips in. Then here we have an unstable equilibrium and nothing else. So it means that our system will evolve to something that maybe the engineers never predicted. But the bad thing is that this cycle, this big attractor exists also here, which means that this is our nuclear reactor. We move it, and then the stability of our desired state is lost. And then there appears something in contrast. Here it was a small amplitude, controllable with the parameter. Here it appears something with large amplitude. And this amplitude now doesn't control. We see that something wrong happens. We switch the parameter back. So the bifurcation happens, this unstable cycle appears, but we are still here. Okay? And then it is that our system becomes uncontrollable. So now we play with the parameters, we go through the threshold, but we are still here. And nothing happens to our system. Our reactor still vibrates and maybe leads to the explosion. So it means that the recovery should be somehow different. For example, we need to blow up this unstable cycle to force it to meet with this one, and only then we will fall down. So the diagram of this unsafe regime is that, so we have the equilibrium, we have the unstable cycle and the stable one. Okay, so when we move the parameter, then here we fall to the big one, the bad one, but to recover, we will have to reach another value of the parameter, and only here we fall back. So this is the hysteresis scenario that probably you heard from magnetism theory, for example. Well, this hysteresis is that transition from one state to another and transition back happened by principally different scenarios. And this is the simple mechanism that really describes existing problems in which planes fall down, reactors explode, or some other catastrophes happens. So this is the core mechanism. So these two different bifurcations, the core mechanism of many catastrophes that really happen. And this is the difference. So safe bifurcation, and this one is unsafe.
I had a question about the stability and equilibrium. So, for example, let's say you're going from a stable system and then it becomes like it goes to bifurcation. Does that mean that your equilibrium state changed, or does it just mean that like the system is far away from equilibrium?
So when we speak about bifurcation in reality, then we need to keep track where we are. So here, from the point of view of mathematician, it is that we we have this unstable cycle disappearing and then appearing.
Okay.
From the point of view of engineering, it is that due to this transition, we now fall here, and then we cannot go back. So for engineers, this is relevant. For mathematicians, it is that here, this is reversible for mathematicians, but for engineers, this is irreversible situation.
So you're saying, so it can't go back to equilibrium? Actually, no. So when you have bifurcation, you move away from equilibrium.
Bifurcations happen. So we have the state space, and we have the parameters space. Yes. So bifurcations happen in the parameter space,
Okay.
and they designate some drastical changes in the state space. So we have two different spaces,
Okay.
and one influence another. And if we have just tune parameters and some equilibrium move, some cycles move, some shape changes, but the whole configuration is the same, then we say there is no bifurcation, and these two types will be indistinguishable in some sense. But if some equilibria collide, disappear, or some two cycles collide, disappear, or two cycles appear somewhere, or some other condition, some pulses appear, or whatever, then it happens bifurcation.
Another question?
I think, well, I have the question, but
Of course.
if I ask, I mean,
Yeah, go ahead.
yeah, so you said that when we, for example, from the engineering perspective, right, we reach the state that we cannot reverse it. So from the engineering perspective, it is important to how to evaluate it, right, to try to predict all of those outcomes, right, because
Yes.
we can have the bifurcation caused by different parameters, right, and so the idea is to evaluate each of those parameters.
Yes, just the realistic picture is that we have here something unstable, here something stable. And this configuration cannot be destroyed by engineering. Just this is our reality. And actually, even the safe scenario has some this and this. So the safe scenario for this transition has some unsafe boundary. So if we are on this big cycle and then we reach another bifurcation, we will fall here. And then it will be really hard to come back. And we will come back either to cycle or this, depending on where this point. So engineers may have some, say, if they look at this at the linear level, like linear approximation, like the Taylor expansion, you should take the first term. It describes good the system, just one term in Taylor. But it describes only this. And if you see, this and this are the same. So in order to understand if here comes stable or here comes unstable, we need to take next terms, usually cubic. But the cubic terms will describe only this, and here this and this. So in order to find this, we need to take fifth terms in Taylor. To find this, the seventh. Well, they're all present. So this is unavoidable. So in order to make this transition safe, the engineers may try to design the system such that this will collide together. Or just to design, it can be, say, gas pedal. To design it such that this boundary will be not reachable. But this, for example, these models that even some students here do bachelor thesis on this topic to study this difference. It comes from the crashes of certain, the same model of fighter planes. In the 90s, in 1 year, there were 3 crashes in Sweden and US of one model of the fighter plane. And the reason was like this scenario that it went to the uncontrollable state, and this state was engineered, so the engineers did not allow to reach this state because they didn't know. Okay, so now it's a question of just physical realization, because this pedal, it's not some abstract tuner that we can move, but it's a pedal that moves in a range. And in this range, this boundary was achievable, but this was not achievable. So it means that the pilot didn't have any chance to recover this plane. So this plane comes in this state, and the only solution was for him to catapult. So no way to keep this machine. Can you imagine? Just because this mathematically he could not reach. Some people say maybe he could maybe it was a solution to switch off and reboot the plane. But can you imagine a pilot doing that in some catastrophic situation? Vibration. So if he was, so the pilot speaks with the dispatcher may ask the engineers may ask the physicists can ask mathematicians. Can you imagine this support line working while he is still there? It's impossible. It's our reality. And this reality is different from the theory. Because in theory, this is nice.
Any other question? Alex?
Well, I will stop, but I have lots, but I will stop.
Yeah, and for your question, so maybe one of the solutions will be to reduce this leg, to make it smaller, like to pull this down, or completely eliminate this leg. But still, this structure cannot be eliminated. So this is unavoidable. So if they eliminate this unstable leg, then they should make also this transition impossible. So this should be limited. But here there will be safety. Yes, but and here maybe if this state is more or less reduced and made safe, then this should be not achievable. And here we need more and more and more terms in the Taylor. And it's impossible to solve analytically. So we have to do everything in computer.
Any other question? Okay, then I hope you enjoyed today's talk. So one thing is, I just want to say is that there are snacks in the back, so when you're done, if you want to take any snack, feel free. The second thing is, after the end of this talk, we'd like to give like small reviews just to ask for your feedback. If there's any voluntary person, just come inside, please. And yeah, thank you very much for today. Please, a round of applause again for Professor Ivan. Thank you very much.
Just do you need the notes? Just. I can generate them. You see no materials.
Professor, do you know who you keep them?
Basically, you kind of expose us. Det var show. Yeah, kinda.
I love that you even think.
Yes.
Yeah, I said it.
Follow चाहिए
And you did it! I didn't even.
Actually, we gotta.
So, some of you want to keep the notes, then you can scan this QR and then you will have the PDF.
Are you? Did you see my lunch? I would like to.
Yeah, for real.
I would like to.
I think we're gonna. I'm gonna. After we get this.
Sorry, my. Yes! Oh my god! Yes!
Girl, I haven't seen you so long. I've been stalking. I've been seeing you tracking.
That's kind of a.
Girl, no, but that's fucking blessed. The determination that you have.
At the beginning of each semester, we go.
Your class is going.
No, I remember emails at the beginning of each semester. Send the email if you want to create your club.
Yes, tell me. Please tell me how you do your.
Push in your inbox.
A while, but now I'm trying to get better at it.
No, it looks so good.
Okay, then it's the
Semester, I was like,
to wait next term.
yeah, I was
You can try to ask Gabriel.
waking up at 5 a.m. while we're doing this.
Where's like which
Really good.
But so there are 3 community coordinators. There's one for each type
Never.
of clubs. For example,
Like,
technical or academical club.
Like-
Sports club, there is a
I'm so
club.
scared I'm losing earrings.
Arts and music club, there is one.
Yeah.
Then you have to ask Gabriel.
No, oh my god, I used to.
Type on Outlook, you will see here. There's one.
Trust me. I dented my water bottle. I had that water bottle.
You don't want in charge of like leading clubs, clearly check.
No, +3.
If she tells you yes, sure. But it's gonna be hard to convince her.
You'll never know. In the first week of having them,
Yeah, maybe it's like wait.
I dropped it.
Next time.
Ripped. Yes.
Me too. I dropped it after getting mine.
Really?
Mine's literally like in the library.
Yeah, no, mine too.
Be the button.
Hey, purple.
Which create a club with on and B.
Really? Oh, that's
These two people.
Today I dropped it in Coughlin.
Okay, then
So now it has like
be the board team in this.
It's not the same. Looking at her.
Yes. No, I literally was talking.
you learn
I was like, bro.
That's kind of what it is. We have to stop being material.
Yeah. It will hit me in the head. I'll be like, guys. No, because my friends were like, we gave you a new water bottle. Did not ruin that water bottle. Did never ruin it. But it's okay. Yeah. Bro, I'll still lose this. Don't trust me.
I need an air tag.
Yeah, no.
I have an air tag.
Really? No, girl. I think I do. No, I lost.
I'm out of the keys.
Oh, your things? No, I've lost a lot of things. I lost like 4 pairs of water bottles. I lost a necklace. No, and they're hurt.
I'm so bad. I'm all over the place, and then I've only been to 2 places.
Yes, that's exactly it. No, the worst thing is I used to do sports. You're mandatory to take off your things. No, you're done. I lost that. Is anybody gonna do the interview?
I'm gonna grab some more time.
No worries.
Professor?
I'll make a video. You wanna do it?
Хотя бы диаграмма.
No, I'm not that social. Well, I'm not that social. No, I am social. You are very social. Yeah.
Just want to ask a question and then.
I don't know. It's not gonna end well.
Yeah, go ahead. Yes. Ask the question first if you want to.
No, what am I supposed to do? Do you have an interview?
لا صافي دير معاه دابا
Да, ты хочешь
هذا معاه بروسيس طويل مده طويله
режим там книги, ара происходит и так далее, там на лампе, да, а на самом деле она может и скакнуть, то есть это как называется, жесткий режим, мягкий радиотехники. Все равно
سجلتنا واش قلتها له؟
пожалуйста.
صافي هو لا هذا معاه مده طويله قال لك
ندوق كيف نقولوا
ندوي فين ولو دابا
Okay, go film right now.
Go ahead. Certainly it's fine.
I'm not asking you a question. Like I want to ask you a question.
Really? Okay, then give me please 1 minute. Professor, is it
Can you please explain
We're playing.
why is it called that way?
Okay.
I wanted to touch reality myself.
Concrete example.
Guys, should we start the interview?
Chaos could actually actually happen. Just
Do
something.
you want to?
Okay.
Okay, you ask the questions that we... I think because I sent you the question. Unless like... Well, unless you really...
No, it's okay. It's I فين بالك
Word, I mean, here the audiovisual, why do you think it's better?
نتفاوض اللعيبة و
This class. Yeah, like this gives me trauma. But like I was like sitting somewhere there for like 1. Yeah, I only come here for the
And then turn off?
like I give you for tutorial. Long time. No different.
just so you can know it beforehand.
You got.